Hello, this is a revision lesson for complex numbers for grade 12. So you're probably familiar with the number system, and of course you eventually get to x squared plus 1 equals 0, which leads to a kind of a strange answer. So we have a square root of minus 1. So what happens is that we actually have to move into a new branch of maths called complex numbers, and we'll have a new variable called I. So I, the letter I, is equal to I, and I squared is equal to minus 1. And from there we'll just develop that a little bit more. And this is kind of cyclical, so it's the same thing over and over after 4 times. So I squared equals minus 1, I to the power of 3, or I cubed, is minus I, and I to the power of 4 is of course 1. So you just multiply them as you go. So you can use them again if you have to find I to the 600. You'll just do it a certain way. And we look at that now with multiplication. So you'll just expand your brackets here, as you know from GCSE. And of course, what we have in this particular case is I squared, which equals minus 1. So in this case, we actually get rid of the imaginary part. So we're dealing with real numbers and imaginary numbers. So the 4 up front is the real part, and the I, of course, is imaginary. And as I just stated, if you have to the power of 5, you can go through your list or try and memorize a certain way of doing it, your own method, and you'll find that I to the power of 5 is of course the same as I, which is, in this case, 2 to the power of 5, which is 32 I. Adding and subtracting is very straightforward, so I've kind of skipped that. Multiplication, you've just seen maybe the I squared part there. So when you multiply two complex numbers, you can get a real number. So we're doing a next complex conjugates. Z is equal to a plus bi, and it has its opposite, we'll say. So what happens here is you can divide. We'll just divide an example here. So what happens is the same as kind of rationalizing the denominator with surds or radicals if you're American. So you multiply across and have the same thing. So 12 minus 3i over 17, and then of course separate them out. So you'll have a real part and an imaginary part. When you're dealing with graphing, of course, you may have some real or some complex. You may even have no real parts, as in they don't cross the x-axis. No real roots, it's called. But we'll see that as well. So z squared, we're dealing with quadratics in this place. So when you multiply this out, of course, you'll get that. And you want to put your real part together, so a squared minus b squared, and then the 2abi is the imaginary part, so separate them out. So when we have an example of z is equal to 5 minus I, you can write it out like this. The best way to do this is actually just to memorize how it works. And we'll actually look at an example now as well in this. So trying to find roots in a graph, it's not really part of the course, to be honest. It's not really there, but just if you want to have a look at Desmos, you can see how that works. And of course, you will do more complex examples. You can use simultaneous equations and substitution as normal. And of course, you'll also come across polynomial kind of type questions. So like Unit 3, where you had a factor theorem and a synthetic division and things like that. Here's an example of square roots. So z squared is equal to a plus bi, and that's all squared. So as I just did, we're going to multiply that out and separate the real from the imaginary part. So on the right hand side, I'm just displaying that, demonstrating that aspect. And just remember that I squared, my I is there, yeah. I squared is minus 1, so you'll end up with minus b squared there. Just be careful of that part. So a squared minus b squared plus 2abi. You can just memorize that again if you want, but there it is in all its glory. So next part on the left hand side, we're going to equate the real part to its own in z squared equals 3, and then of course the imaginary part is 4i, and from there we have to find a kind of way of doing this. Get rid of those i's, you don't need them. ab equals 4 over 2, which is 2, so b is equal to 2 over a, and then substitute that back into the other formula, the other equation. And from there you'll get a quadratic, If you get something beyond that, a to the power of 4 in this case, it's a hidden quadratic, so you can use a substitution like y equals a squared and substitute it in and then change it back, or you can just do it straightforwardly using your double brackets here, as I will do there. So you'll end up with a squared for both. A squared equals 4 and a squared equals minus 1. Minus 1 will be a non-answer, and a is equal to minus or plus 2. So sub in again to get b as well into one of the equations. So you'll end up with 2 plus I and minus 2 minus I believe. That's clear there. So there's square root kind of questions. You will also have roots of quadratics. You can use your quadratic formula, your completing the square techniques. Remember, the solutions are always complex conjugates. So you'll have the 5 minus I will always have its 5 plus I, and so forth. Okay, let's move on to Argand diagrams. So in this case, we don't have an X and Y coordinate grid, Cartesian coordinate grid. We have real and imaginary numbers. So we just see one there. So this is 2 on the x-axis if you want, and 3 on the y. So it's 2 plus 3i, and that's how that works, and that's where they come from. And I'm writing this down just 90 degrees anti-clockwise. You would have something, the I part will always be there, we'll say. There's z and w. Now z times w, you can do the algebra of that out and then graph it, of course. On the right hand side you'll see that. So when you've done that out, we're going to find then IZW, which should be 90 degrees anti-clockwise away. And that kind of thing will come up later. Oh, leave it, it'll be fine. So there's our lines. So the next part, IZW, so there's a cock crowing. Brilliant. So minus 4 plus 8. So you can see that that's 90 degrees if you want to have a check of it there. You can see the way it's almost a reflection in some ways. There's a kind of a mirroring aspect to the way the numbers have changed with the 4 and the 8. And then the last part there, minus a half minus, or sorry, plus 1/2, yeah, plus 1/2 minus I. So remember, you can have no roots and still have complex roots. So you're going to have answers in these things that seem a little bit non-intuitive sometimes. So you have to get used to this concept and take your time with it. So moving on from that, what else we got? Any more Argand diagrams? I'm going to move on to the modulus argument form. You know modulus already. Think of it as the hypotenuse in a way. You used it in, it's actually your own topic at the beginning of Pure 2. You have a new thing called an angle. So the angle there, instead of data, we'll say, is an argument. So arg z. So mod z, you know already, and arg z. Again, maybe for mechanics as well we've done. So you'll know that it's tan b over a, and it's always in radians as well. Well, I think so. Yeah, it's always in radians, isn't it? I had to think about that for a second. So, modulus form, just redraw that there. So mod is, the way to think of it is Pythagorean, of course. Y over x. X squared plus y squared, and that's equal to mod squared. So the root of that okay, so z, let's say an example, z is equal to 2 plus 2i. So in terms of the graph, I might make it 2 minus 2i actually. Yeah. So think of your cast system, like CAST, so where they're positive for cosine, sine, tan, and just go along, you're going in a certain direction, aren't you? So this one, for instance, is plus 2 and then minus 2. So, 2 over 2 is easier for this one, but of course it's anti-clockwise, so it's minus pi over 4, so be careful with that. You could do a bunch of examples on that just to practice that if you're not really familiar with it. Just check for each one. Do your like less than 90 degrees, and do the second quadrant, sorry, and the third and fourth quadrant as well. Polar form. Okay, let's move on to polar form after modulus. So polar form is its own thing. Excuse me. We're using the modulus and the angle here, of course, from what we just stated, but it gives us a new form. The polar form does. So it's or times cosine data plus I sine data. So you need to remember that as an equation, we'll say. From that, you'll also have the exponential form, which is mod e to the arg I, but it's equal to or and then e to the I data. That's the one you remember. And you'll be using that for different things. You'll be multiplying and dividing the modulus argument form, and you'll be doing conversions. So the conversions, I'll do one example now of this. So Cartesian, what we had, let's say, was 2 plus 2i. We'll do that. The polar form of that, again, is 2 root 2 and bracket cosine pi over 4 plus I sine pi over 4. So just think about the change there in terms of the angle. We got an angle out of that. And also the exponential form then was the same, so 2 root 2 e to the pi over 4i. So I always goes after, although it goes before in the Euler formula, but that's just a convention, and maybe just a little difference there, but I always goes after. And also think about cosine as an even function and sine as an odd function in terms of those things too. It might help you. Next part, multiplying them out. This is just something just to remember. It's not very exciting looking. Just think of it in terms of, especially, it's the same as your powers. You know, when you add, you actually multiply, and when you subtract, you actually divide. Think of it in that form. In terms of Z1 times Z2 and Z1 divided by Z2. It's pretty straightforward, actually, even though it does not look very nice. So when you're multiplying and dividing it in the modulus argument form, be careful of that as well. Just back to polynomial work as well. You know, use your factoring, use your intuition, guessing. You know, equating coefficients is often a little bit of a guessing game. Use your calculator, let's be honest. Complete a square, quadratic formula, and also synthetic division. We use that too, wherever we need. Loci, so the last part of this, which is quite expansive actually. So loci, you will come across bisectors, you'll come across circles, and also trying to find angles, so the smallest value of the argument z. There's a circle there, so mod z equals or the radius. That's straightforward. But when you see it in a more expanded form, so it's like z minus 3 mod z minus 3 equals 6, for instance, you have, like, it moves, so it's not like at the origin, it moves like 3 places, let's say, and the radius of that circle is 6. So you'll have to remember that kind of idea, and you should probably also rewrite, as I've just done, rewrite the bracketed parts if you want, because it gives it in a certain form. It's z minus, it's always z minus, so if it's z plus 4 minus 2i, that would be z minus bracket minus 4 plus 2i, close bracket. So of course, as I said there, just a translation as a movement. Okay. So just changing the position. Next, on to the same idea, just want to show it in more detail. So when you're doing this, I'm just going to show the algebra as well. My pictures won't be amazing, but look. So z minus 3 minus 6i, just rewrite that, you know, but you'll have 3 plus 6i. And of course, that picture actually isn't very accurate. It should be up further. The circle should be up further to cover that 6 in terms of its distance. But there's the idea. So the radius is 3, obviously, and your position is 3 plus 6i on the grid. Okay, I'm going to move on to bisector. We got bisector and the smallest value of arg, the argument. Those are the last parts, in a sense. There's combinations of all this stuff as well. It seems like a lot, doesn't it? But this is the last topic on your course, so I suppose in a sense it is a very difficult one. It's also a very new one. It's kind of its own thing. It's something very new. You would probably not have come across most of these concepts in any way before this course and this year. I'll just do another example there of that. So just to show it how that changes, just to make sure. So rewrite that so you know where its position is. I haven't really covered like the x squared plus y squared equals r squared, like rewriting it as the circle equation. I might do that for the next video. Here's an example. So pi over 6 is less than or equal to arg. Z minus 3 plus I is less than or equal to pi over 2. That looks very daunting, but just take it step by step. So rewrite that middle part. So we know it's like 3 minus I. So we're going to place it at 3 and minus I, as in minus 1 on the y-axis if you want. That's the imaginary line. So it's just down below there. And of course, do a north line. Same thing as like maybe for bearings. And you'll find pi over 2. Well, you know already what that is. Same as pi over 6. 30 degrees. I mean, you're probably past using degrees now. You've been using radians for 2 years. So that's what they are. And of course, you have to shade a certain part probably for these kind of questions too. Again, that probably just you need to go and practice some questions on that to see it in more clarity. Again, this is just a little revision, quick little look at it. So next part, the smallest value of z. Well, this is straightforward, I suppose. This is kind of intuitive. So like your modulus is the line, and if it's going through from the origin to the circle, you're going to have that difference. So the mod is the full line, the radius is just there. What's the smallest length there? It's going to be the difference between them. So I'll just draw that now for you. So the smallest value of z is not too difficult there, but the smallest value of arg, which I'll do in the second graph, maybe a bit more. So radius is there, and modulus is obviously the longer part there. So, how do you the difference between them is what you're looking for there. So if they ask that question, and the smallest value of arg is probably a lot more difficult of a question. Let's say you have the modulus drawn out as well to the center of the circle. So you're going to maybe create a number of triangles. It depends sometimes, but generally 2 triangles. It could be easy actually sometimes just having one of them. So there you can see I'm going to draw just tick tick down. So you've got the right angle triangle. And of course, you can look at it with your trigonometry is in a sense. Opposite and adjacent, you got tan. Yeah, so the green angle there. I'll put that in on the other graph as well. So tan, beta or alpha. Choose one. And of course, you can do the other triangle. You can kind of create it out like a tangent there. You see the way it goes like that? It's obviously 90 degrees tangent to the circle. So do that out like that, and you'll have another triangle. So you're trying to find the difference between them two, of course. And that would give you what you're looking for. And that would be sine, I think, generally there. So modulus meaning the longer side. So alpha you can use in that case if you want, or beta. I would use alpha in the first one. It doesn't matter. It just so using sine opposite over hypotenuse to find that there. So if you can see that properly there, the red one there is the second one, and the green dot is the first one. So tan minus sine. Bisectors is the last part there, I think, of this. So you'd have to circle and the bisector question together, and that would be a difficult question. So rewriting them there, as I stated before, to make it a nice way to look at the positions. So z minus is always the formula that it takes. So minus 2 plus 8. And let me just figure out my little drawing here first. My graph. Make sure it's in the middle. Yeah. So yeah, just draw that out, and you're going to get these 2 points, and you have to do your bisector from there. And to be honest, there's generally a circle involved as well. So line that up. So if there was a circle as well in down and below there somewhere, you're kind of looking at a point. So you'll do a bisector through that particular point. It might not go through the center of the circle. It might just depends on what it is. But let me just draw a circle as well, actually, just to make it palatable. So look, the idea when you have something like that, so you have your bisector equations there, and then of course you'll also have the circle that you've drawn, and you're trying to find something, and eventually you're probably also trying to find the smallest value of the argument as well. So all these bits will come together in that way. So the circle, bisector, and arg z of that, and that's pretty much most of what you'll be doing. You're trying to find possible values of things sometimes. Again, splitting up your real and imaginary parts. To find roots, you'll use the quadratic formula or complete the square. Using your polynomial skills you learned from Unit 3 to factorize. In some cases you can't factorize, so you've got to use those skills I just mentioned. Use your calculator and equate coefficients in that sense, equating different parts. If you cannot do that, of course, again, use synthetic division, dividing z minus 3 into z to the power of 3 minus 6z squared, and so on. Instead of x's, you'll have z's in this case. So that's the difference there. With modulus argument questions, I think you have to just practice them a little bit and see the transitions. So converting into polar form and the exponential form is just something you have to do a bit of practice with. A good way to do it actually, it's not on your course, but go look at the Maclaurin expansion and how that relates to Euler's identity, because it's often known as the most beautiful formula, of course, but you can see how the cosine and sine of x series work. So sequences and series, and they both alternate, but they both happen to turn out perfectly as the e to the x, which just one of those things. Maths is very neat sometimes. That's just the way it works. So Euler's identity is a little proof you can go look at for that maybe, and it leads into that formula I stated, like e to the I pi plus 1 equals 0. But in this case, you'll be using the exponential form of e to the I data is equal to cosine data plus I sine data. And I think that is about it.